Alright, video number 2. We're looking to graph the equation here and then answer the questions. So we're graphing the equation. You want to think of it as y equals. So on Desmos, you would type y equals, and instead of t, you're going to type x. That 2 looks a little misplaced, so I'll rewrite it all for you. Y equals negative 16x squared plus 24x plus 1. So the ball that is kicked follows that equation where h is the height or y is the height and t is the amount of seconds. So t is time. Our picture won't necessarily be what the ball is doing, but it'll show it, the height in relation to time. So let's go ahead and graph it. If you want to go to your Desmos and graph it, I'm going to pause and show you what I get on Desmos. So if you want to pause it now and get your Desmos calculator up and type in that equation. So here we have the Desmos screen. You can see the equation is in the upper left. Notice my window is basically 10 by 10 by 10. If I can. And then I've highlighted the important points. So we got the maximum at negative 0.75 for x and 10 for y, so a maximum height of 10. And then it hits the ground back at 1.541, so it traveled about a second and a half. All right, so we've got this. Let's go over and answer the question. So if you need to pause, go ahead and pause now. So this box here is where we're going to write our graph in. So we're going to sketch our graph, and mine's a 10 by 10 window, so I'm kind of something like this. Just needs to be close. Over here you have the x-min on this side. It's basically where your window is. Our window on the left side stopped around negative 10. Your x-max, our window on the right side, stopped about 10. I think our y-max on our window was about 15 on mine. Yours might be different. The y-min on my window was around negative 10, so this just needs to be close. That tells me how accurate you can draw it if you're, it's hard to explain. We'll talk about it when I get back. So question A says, how many solutions of this equation make sense if you're trying to find the amount of time it took the ball to hit the ground? I'm a little fast, sorry, so if you need to pause, go ahead and pause and fill in those spots. So how many solutions make sense? Only one solution makes sense, because we know that this point right here is where the ball starts, and this is where it stops. So in terms of hitting the ground, it only hits the ground where that blue highlight is. So one solution makes sense because it starts above the ground. Let's see exactly where it starts, huh? Starts at 1 foot above the ground. 1 foot, right? 1 foot above the ground. Okay, if you need to pause, go ahead and pause. I'm going to move on. The ball is caught 3 foot off the ground. What is the most reasonable answer for how long the ball traveled in the air? Well, this is what we did on this, is we said let's find when y is 3. So let's go to our Desmos, and we're going to add an equation in. So I go plus expression, and I want the 3 foot. So y is the height. So where is y 3? If you need to pause, go ahead and pause now. And now looking at this, we now are looking for this dot here. Let's turn the others off. So you notice the second number is 3, so y is 3 when x is 1.4, and x is the time. So I'm going to go back back and fill that in. Go ahead and pause now if you need to pause. So how long is the ball in the air? About 1.4 seconds. Okay. All right. Go ahead and pause now if you need to go back and fill some of that in. I'm going to go on to number 5. Number 5 says a paper wad is thrown at the trash can. The equation -16 h equals -16 t squared plus 18 plus 2 describes the travel. So when we graph it, we're going to change that h to y. So we're going to have y equals, and we're going to change the t to x. That's what our calculators deal in. And then we're going to graph it. So I'm going to go back to my Desmos. And you can see me type it in this time. So I erase these and then add another. Y equals -16x squared plus 8x plus 2. I'm going to double check that. 8x plus 2. 8x plus 2. And now I don't need quite as much graph, so when I come over here, I can zoom in a little more. And now notice my window. You see that my window is basically positive and negative 5s on all ends. My important points are how high it is when it leaves, the 2 feet, how high it is at the maximum, 3 feet, the 0.25 is the time. When it hits the ground, so the y is 0 at ground, so the height is 0, the time is 0.683. If you need to pause, go ahead and pause now. Alright, now I forgot what my graph looked like. Let's go back to Desmos. Okay. So I'm going to go ahead and sketch what my graph looked like. Looks something like this. And our X-min, our window was basically basically -5 on the left side of x, +5 on the right side with x, -5 on the bottom with y, +5 on the top with y. How many solutions make sense? So this is the exact same answer that we had above. One solution. Because it leaves. I should probably say starts, sorry. It starts. And how high did it start? It starts 2 feet off the ground. So it starts 2 feet off the ground. Room, huh? Alright, sorry, that's a little sloppy. If you need to get caught up, go ahead and pause now. I'm going to move on. Alright, what is the total time the paper is in the air? Our total time is this last point, the 0.683 is the time. The 0 is the height, so when it hits the ground, it's about 0.7 seconds. So I think that's pretty accurate. Total time, we're going to say about 0.7 seconds. What is the reasonable domain? Well, in this case, domain is x, right? So what are our reasonable x values? And we're going to go, it goes from 0 call it 0.7 because we rounded. So let's, and then our notation is 0, 0.7. If you wanted to be more accurate, you could put 0.683. And we'll say the D for domain, put a colon, and put it in those brackets. So if x goes from 0 to 0.7, we put that in the bracket like this, and that's our domain. The reason that's our domain is because that's the amount of time that the paper wad is traveling, and if it is not traveling through the air, then it doesn't match the equation we graphed. If you need to pause, go ahead and pause now. I'm going to move on. Alright, we've got a jumping squirrel. We're in terms of y and x, so that's good. Let's go to our graphing calculator and see what we get. So negative 0.2 and 0.7 are coefficients. So I'm going to clear this out, and I'm going to add an expression, and y equals negative 0.2x squared plus 0.7, was it? Let's double check. Yeah. Oops. Sorry about that. That makes a little more sense. 0.7x. Alright, so my window, I think doing the 5s again is fine. Back and let's go ahead and graph it. Look at that one more time so we can be more accurate. So our x-min was around negative 5, x-max was 5, so that's the left side of the x, the right side of the x. The bottom side of the y was negative 5. The top side of the y was around 5. I want to double check that. It's too high though, isn't it? That's okay. It's close. Not perfect. So if you need to pause to get that sketched, go ahead and pause. Again, I'm just trying to get this sketch from the Desmos. Alright, find the total time the squirrel was in the air. Let's go to our calculator. And let's look at these important points. So this, remember the x-axis is the time. So at time 0, the jump is starting. At time 0.613, the squirrel is 1.75 feet in the air. And then it lands at time 3.5. You can see that height there is 0. So it's about, the time is about 3.5 when it hits the ground. That's misstated. Let's call that seconds. So find the total time. I think up here, sorry folks, better fix this. X is the time, not the horizontal position. So total time was in the air, 3.5 seconds in the air. Can the squirrel jump over a 6-inch log? Well, let's go double check. But it looks like its maximum height is 1.75 feet. So with 1.75 feet, it should be able to jump over a 6-inch log. So we would say yes. Max height, that's the word height, is 1.75 feet, which is more than 6 inches.